think we'll go ahead and get started. So I'm Nayoka. I was the one emailing you guys, and we just want to say thank you for joining us for the Lunch and Learn today that will focus on optogenetics. So I thought I'd just start by showing some data from the survey that you guys submitted, and just to give you an idea of the other people on the call. So you might remember these questions from when you registered for the event, but you can see that about 2/3 of you guys have previously used Optogenetics, and another part of this question was which system. There's a wide range of systems that you guys have used, and about 1/3 of you have not used Optogenetics in the experiments before. And then a couple of the other questions were about the experimental design. And you can see that there's a range of what you guys want to do with Optogenetics, and we'll talk about the 3 different kinds in the presentation today. And one thing that most of you have in common is that you'd like to record behavioral tracking at the same time as your optogenetic stimulation. And so we'll also talk about that during the presentation. And you'll notice some of the other questions that were on the questionnaire. You'll see those pop up throughout the presentation. We tried to use the answers of those questions to kind of guide the presentation to make it more relevant to the people in attendance today. So there'll be 3 speakers, and it's kind of broken into to 3 parts. So Nafi will start, and he'll go over the overview of the Plexbright system, which is the name of our optogenetic system. And then he'll talk about choosing the appropriate components based on the type of experiment you're planning. And then Kristen's going to go into a little bit more detail about that. Once you have your components, how do you get them all connected? And she's going to talk about combining optogenetics with behavioral tracking, and then also combining optogenetics with photometry. And Damon will finish the presentation going over the Radiant software, and then talk about combining optogenetics with electrophysiology. So I think you'll see after the presentation how easy it is to get started with Plexbright, and then also how convenient it is to implement some of the more complex experimental designs that you've mentioned in the survey that you completed. And just one last thing before Nafi starts is we really hope that by doing these small virtual presentations, you'll feel comfortable asking questions. And so there's several ways you can ask questions. The first being just unmute your microphone and ask the question. If you'd rather, there's a raise the hand feature in Zoom. You can just use that, and one of us will notice and let the speaker know that there's a question. You can also use the chat feature to type your question, and then we'll answer that. And then after each speaker finishes their portion, we'll have a question answer session at that point, and you can wait until then if you would like to ask a question as well. All right, Nafi.
Okay, I'll go ahead and take control of the screen then. All right, can everyone see my screen? Okay, excellent. All right, so the first step in setting up an optogenetics experiment is, of course, choosing the equipment you're going to use. So I'm going to go over your options and light sources and the benefits and disadvantages of each. Help you give some tips on selecting the controller. Also going to go over kind of how the systems differ if you're doing a fixed subject versus a freely behaving, and also as well as going how to choose a fiber and a fiber stub and what the different specifications for those items mean. So the main advantage of LEDs is that they're much more robust, they last longer, and they're harder to damage and break. They're also lower cost. They're eye safe. The reason for that is LEDs do not use collimated light like lasers, which I'm going to go over a little bit about what that means. So if you accidentally turn on the LED and it shines in your eye, it's not going to cause retinal damage like a laser can. And also too, LEDs have a much wider range of wavelengths available. And finally, they can also be made very small and compact, which is really handy if you're going to have behaving subjects. And for lasers, they have a single but significant advantage, and that is that they can output much more power compared to an LED. So basically, I would recommend determining how much power is needed, and if you can do it with an LED, then an LED should be used. Otherwise, then your only option is a laser. However, it should be noted that many publications use lasers with non-ideal wavelengths, simply because LEDs were not available yet. For instance, 630 nanometers is commonly cited for being used with redshifted options like Crimson R or Reach R, even though the peak wavelength of those proteins is around 590 nanometers. Or 532 nanometers is often used for RKO rhodopsin 3, even though it has a peak around 566 nanometers. Ideally, you want to use as little power as possible at the wavelength of highest sensitivity, as excess power can cause heating in the neural tissue. At low amounts of power, it can increase activity, which can be particularly problematic if you're trying to inhibit activity. And at higher amounts of tissue, it can even cause tissue damage. In all the conversations we've had with customers, we have found that the majority of experimental designs can be satisfied with LEDs. As I mentioned, lasers use, they're pretty special in that they use collimated light. So basically all of the photons all the light coming out of a laser, all the photons are basically coming out in parallel. That's the reason why lasers produce such a tight focused beam of light. LEDs are more like any other standard light source. It's basically those photons are coming out at random angles. So depending on your experiment, this could be an advantage or a disadvantage. Basically, if you are trying to target a very small area that's roughly the width of your fiber, then a laser will allow you to really just focus it on that area and only deliver light to that specific region. Whereas if you're trying to stimulate a more diffuse area, the light from an LED will exit the fiber at a multitude of angles, allowing you to stimulate a larger region. So we'd asked what kind of experimental design that you plan to use. It looks like the majority are using freely moving animals, but also significant amount using head fixed or anesthetized subjects. And also a few people using in vitro. So next, let's go over kind of how the system differs depending if you have a freely moving subject or not. So for the most basic system, you just need a waveform generator and an LED or laser driver, the light source itself, and for most recordings where you're just going to record from a fixed subject, just insert the fiber and they're not moving. You can just get a fiber itself with a bare fiber tip and just insert that directly to the brain. However, if you have a freely moving subject, then you need some way to deliver that light to the subject where the patch fiber isn't getting twisted up. And so there are a few different methods of doing that we'll go over. And then also too, if you need to disconnect the animal, like basically if you're going to be recording for a while, you need to be able to disconnect the subject from the experiment so that they can feed and sleep in between recordings. And then of course, if they're moving around, you need a way to have an anchored connection to the skull that won't come loose. So Plexon offers two LED controllers, the single channel LD1 and a 4-channel controller that comes with our Radiant software. So the LD1 single channel driver requires an external waveform generator. So whether you're using MATLAB or if you have a function generator or a TTL pulse generator, you can use any of those. It has both a digital input for receiving TTL pulses to deliver light pulses based on that. There's also an analog input where you can create arbitrary waveforms. If you do not have a way of generating your waveforms, then using our Radiant software with our 4-channel controller gives you a way to create all sorts of complex waveforms or long trains that can either be triggered externally or internally in the software. So for basically our non-moving subjects, we're going to use our tabletop LEDs. And then we have a few different options for our freely behaving subjects, either using a patch fiber and a commutator, or mounting it on the head or the wireless LED. And I'm going to go over in just a minute basically what the advantages and disadvantages of those systems are. And we'd also asked you, what frequencies you guys plan to use. See that the majority are using 470 nanometer. Not surprising. Channel, that's namely, I'm assuming channel rhodopsin 2 and its mutants, which is the most commonly used protein. Also see a lot of people, it looks like, are using archaeorhodopsins and also redshifted channel rhodopsins. So that's very interesting. Okay, and so as I mentioned, the tabletop LEDs have a wide array of wavelengths available, and this is what Plexon offers. So now, if you have your freely behaving subject, the first option is to have commutator-mounted LEDs. The Plexon design is pretty unique in that previously what people would generally do is they would use what's called a fiber optic rotary joint, and that they would connect a cable to one end and have the cable go to the other, and that allows the two fibers to twist independent of each other. The problem with rotary joints is that while the cable twists, the amount of light that transmitted varies. So you get a non-consistent power source to your subject. Plexon solves this problem by mounting the light sources on the animal side of the commutator. And it's just basically commutating the power source to the LEDs. That way, no matter how the animal moves, you always get a consistent amount of light to your area of interest. So the main advantages of this is that this solution offers the least amount of weight on a subject's head. So if you're trying to get the animal to behave as naturally as possible, this has a lot of benefit. It's also very simple to do concurrent electrophysiology, and we have a commutator that can pass both the LED signal and electrophysiology signals at the same time to make that easy. You have your full choice of wavelength, same choice of wavelengths for the tabletop LEDs is available. And since you don't have any batteries involved, there's no limit on the recording time. So you can record for hours or days or stimulate for hours or days at a time as needed. The only drawback is that you do have to put a patch fiber between the light source and the subject, which does cause some power loss. So to address that, we have our head-mounted LEDs. These still require tether to the commutator because it requires power. But by putting the light source right on the animal's head, you eliminate that power loss. And then also, like with the commutator-mounted LEDs, since it is a continuous power supply, you also don't have to worry about batteries or recording time. However, now that you put in the LED on the subject's head, you're adding weight to the subject's head. And so especially with smaller subjects like mice, then that's more likely to affect their behavior. Also to the, in shrinking this LED down, that also results in limited wavelengths. There are only 4 available, which is the same thing for the wireless LED in blue, green, lime, and orange. And going to the wireless LED now, like the head mounted, no patch fibers needed, so you also get a very bright signal. And the main advantage of this is that you don't have a tether to get tangled up. So if you have the animal going through some sort of complex environment where there are overhanging objects or something that would tangle up a cable, then this would basically be your only choice. However, since you now are adding a battery and a receiver transmitter to the LED, this puts the most weight on the animal's head. So unless you absolutely need it because you do have this complex environment, I would advise looking at the other solutions. And of course, too, the battery, now you have to worry about the battery, making sure that's charged. So if you're recording for a longer amount of times, that could limit stimulating for a longer amount of times, that could limit your experiments. Another thing to note about the wireless is that you are not transmitting power directly to the LED. That's handled on the LED unit itself. So instead, you're sending the signal to a transmitter, and so that transmitter accepts voltage. If you try to use the LD1, which is only a current driver, it expects a LED on the other end. It'll basically try to just ramp up the current because the input impedance on the transmitter is so high, and you're likely to damage the transmitter. So you don't want to use that. On the other hand, the 4-channel Optogenec driver does have a voltage mode, so that it is compatible with the HELIOS. Okay, and so also in asking what kind of subjects you have, see that rodents dominate with a slightly larger set of people using mice over rats. But it's also pretty cool. I see that we have some people doing non-human primates and even bats and ferrets. So yeah, that's pretty cool. So in selecting your fiber, basically the first thing is how you're going to terminate it. So there are two standard terminations for light sources, and this is also true of lasers, is the FC connection and the LC connector. The FC connector is what's used on our tabletop LEDs, whereas we use the LC connector as a standard connection for our commutator mounted LEDs to reduce the weight. On the animal side, assuming that you're using a freely behaving animal, you can terminate it with a FC ferrule. So this is distinction from the connector. This is just using the central plastic part of the connector itself to provide a way to connect to the animal skull. FC ferrule is 2.5 millimeters in diameter, whereas LC is only 1.25. The thickness here does not affect the amount of power delivered to the subject. That is determined completely by the core that's inside it. So the only real difference is that the 2.5 millimeter are easier to handle, but at the cost of they take up more real estate on the animal's head. Most people will generally use the FC, the 2.5 millimeter ferrules with rats, and the LC ferrules with mice, but it's not exclusive. You can use FCs with mice and LCs with rats. Depends on your preference and what you're doing. So then you have your specifications regarding the core size and the NA, and of course length is pretty self-explanatory, but that's also an important specification. So it's kind of important to know about how the fiber is created, what its architecture is, and basically you have an outer jacket which keeps light from coming in or out of the fiber. You have a central transparent core, which actually carries the light, and that's actually surrounded by what's known as cladding. And while that's transparent, it is not designed to carry the light. I kind of go into the physics of this and how the core and the cladding kind of determines the NA, the numerical aperture. And I have a blog that forthcoming that's going to describe that. But basically, in simplest terms, you can kind of think of it as an acceptance code. So Plexon offers two fibers. They're both high NA. Since the LED is emitting non-collimated light, you want to have as wide of an acceptance code as you can to collect as much of that light as possible. So we offer two values, 0.66 and 0.50. The 0.66, as it collects more light, we call that the high performance. And then the 0.50, we call the high durability. And the reason for that is it has a much smaller bending radius, basically only 2 millimeters compared to 25 millimeters. So basically as the animal's running around and that cable's getting, forces acting on it, with a high durability, it's much harder, it's much more unlikely for that fiber to be kinked or damaged. And then the length has a very, has an effect on the power. Obviously, the longer you run the patch fiber, the more loss you're going to get along the fiber. So that's an important consideration to consider when you're setting up your experiments and choosing your equipment. And Plexon has a resource for this that basically shows a common light measurements for for equipment, depending on what wavelength of light you're using, and if you're using a high performance versus a high durability, basically, at the tip of the fiber or the fiber stub, and it's a useful resource. You can find this if you go onto Plexon.com. If you click on the Plexbright systems page under resources, there's the Plexbright data sheet, and this can be found there. Another thing to take into consideration is that rodents like to chew on things. And of course, if they chew on your fiber, that's going to ruin the experiment. And you'll have to replace a patch fiber. So we offer two jacketing options to put around the fiber to protect it. The first is our monocoil wrap, which is very nice and flexible. It doesn't add too much weight or stiffness to the fiber, but it does add some. The drawback being that since this is a helix, basically the determined wrap, given enough time, will be able to get its teeth in between these, in between the edges of the helix and still damage the fiber. So for those very hyperactive rats, we have this armor jacketing, which much more robustly protects the fiber. It doesn't have any gaps in it, but it does greatly increase the stiffness. Both of these, since they do add since a little bit of this one, of course, armored much more so, since they do add some stiffness to the fiber, that should be a consideration if you're using mice. Oftentimes mice, people will just use the fiber, the naked fiber itself to make the lightest weight and most flexibility so as not to inhibit their behavior. Okay, and then let's talk about the fiber stub. Of course, if you're just doing acute recordings in a fixed subject, you can just take a fiber with a bare end and just stick that directly into the animal's brain. Gives you the most direct approach. But of course, if it's moving, you need a way to be able to disconnect it. So we have our fiber stubs that connect to the end of the fiber using a ceramic or a stainless steel sleeve. And the fiber stubs come in the LC and FC sizes to match our fiber offerings. And also a thing to note about, as I mentioned, that the LC ferrule being a little bit more difficult to handle just because it's being tiny. For that, we have this magnetic option that puts a magnet at the end. So instead of worrying about having to seat the sleeve and seat both ends into that, basically it just has a strong magnet on it that will attract itself and snap onto the fiber stub, as you can see in this animation. Are there any questions?
Hi, Nafi, I have a question. I saw your commutator, you can mount two LEDs on it. Mm-hmm. I was wondering if those are interchangeable. Can you decide one day to switch easily from orange to green on one of those two LED modules?
Definitely, and that's actually kind of the main reason why we design it in this fashion. It's kind of hard to see here, but these are actually the LEDs are mounted to the commutator with magnets, and then there's a little power cord here. A little bit, Chris is going to show how that connects and disconnects, but it's made to be very easy so that you can easily swap out different wavelengths to do use different types of proteins.
And you said those with the LEDs attached to the commutator are different, but for behaving animals, it's preferable to have the LEDs on the animal's head?
That's just if you need very high power. So from that table I mentioned, you can kind of see that basically, assuming you're using a 1 meter fiber and which type you're using, how much power will come out depending on which fiber stub you're using. If you need more power than this, then you'll want to consider a head-mounted LED. In this same document, we also have the listings for the power from the wireless or head-mounted, which is significantly higher.
All right, thanks.
Yeah, my pleasure.
I have a question related to implants.
Mm-hmm.
So are the only options the single core? I'm asking because I work with the adolescent mice, so they're very small, and also midline structures, prelimbic cortex. So I have in the past done a dual core, sort of one, fiber cannula, but then two, I guess, fiber optic borosilicate implants. Because that's the only way to get like close enough together.
We don't produce them. We found that one of the problems is getting it to mount easily with those tools. If you were trying to make a single kind of connector, you can have spacing issues. However, since even though those dual ones, even though they're not produced by us, since the majority of companies also just use a standard LC or FC ferrule, our fibers will mate to them.
Okay. So this is probably specific to the implants I have, so I apologize. This is not relevant to anybody else, but the dual core implant I have actually has like 2 little holes in the top for the light to shine through, and then I have it's half of my opto system is from Plexon, half is from Doric, and so for the Doric system, it's like this also dual, bifurcated patch cord, and so it shines like 2 sources of light into 2 holes. So I tried recently to use it in my Plexon system because I had the implants and the mice. And I was hoping to use my Plexon LED, and I wasn't sure if like a straight up, I guess FC connector would shine enough light through the 2 holes, but it sounds like it should.
Yes, so basically then their fiber is just 2 cores going up inside a single jacket, and then the 2 cores are go to the FC connection.
Yeah.
So yeah, it should. Of course, then the fiber though, then you're going to have to just be careful on the NA for the numerical aperture on that, since basically it's not. Normally, when you the kind of the advantage of the FC connectors and the LC connectors is they perfectly align the cores with the center so that you're gathering as much light as possible. So if you're having this double core side by side, you're going to end up with some power loss. If at the end, the power, if you're measuring that it's coming out and it's more and it's enough power, then it's not a problem, but just something to consider. By chance, does Doric offer maybe a bifurcated cable that has 2 separate fibers that you can connect it to light sources, and then comes together to connect to this? Because if so, that would.
I think they do. Yeah, I think that's one of the options that I do not have. So that would be if I want to continue with this system.
That would just be if with the current fiber you're fighting,
right?
Not getting enough power. Yeah.
Okay. Thank you.
Yeah, my pleasure.
So actually, I used to make the 2 fiber paths. So I just use the length to focus 2 light beam into the other end of the patch fiber, but it's a pure homemade version. So, but it works. So I still have power loss, but if you focus with a length, that it should. So I went to fiber photometry with this system, so it's durable, but not that plug and play. But you have to make it yourself.
All right. Well, then if there aren't any other questions, I'll go ahead and hand off to Chris and Mark.
All right. Thank you, Nafi. Find the right screen to share. All right. Is everybody able to see my screen?
Yes.
For the most part? Okay. Thank you. All right, so Nafi went over the basic components of an optogenetic system, which are the driver, the light source, and then the fiber stub implant. However, how you'll connect these different components depends on what your experimental setup is going to be. So I'm going to go a little bit more into actually connecting these different components and some of the different considerations for these different setups, and then again touch on considerations for different animal models. So let's start with an in vitro model. Most people prefer to use the 1-channel controller, which is a simple on-off switch. And then you can control this switch through a TTL or analog input. And so this controller will be connected directly to an LED through a BNC cable like this one. And this is a tabletop module, which, as its name suggests, is going to sit right on top of your lab bench. And then the LED will be connected directly to your patch cable. patch cable I have here is a bare fiber end patch cable that you can stick directly into the animal head. It is covered with a plastic protector just because I didn't want to break it when I was doing this demo. However, you can use a patch cable that ends in a ferrule if you want to attach, detach, and reattach to an animal multiple times. This is a fairly straightforward setup. So now let's talk about if you want to do a model in freely moving animals. So we generally recommend the 4-channel optogenetic controller because it works with radiant to deliver patterns of stimulation, and it's also more versatile with digital inputs and outputs to integrate with other systems. So again, this controller, you can control up to 4 LEDs independently or 4 channels independently. And if you are using freely moving animals, you're going to want to use the commutator like this one, which acts as a swivel to prevent severe twisting of your patch cable, which will fracture it and greatly reduce your power output. So you can connect 2 channels to this commutator, which will control 2 LEDs independently. Connections are pretty tight. However, if you want to do bilateral stimulation, you can connect 1 channel on the controller to both channels on the LED, or on the commutator, which will control 2 LEDs at the same time with the same pattern. So these are the magnets on the bottom of the commutator, which will connect to the compact LED, like this one. And you very simply, you just plug it into the commutator for power, and then just snap it on. And finally, you will snap in your patch cable directly to your LED. And then you can turn on radiant to deliver your pattern stimulation. So this patch cable and the patch cable I showed with the in vitro setup both have a monocoil armoring, which is pretty flexible and still pretty light, and it's the minimum we recommend for rats. However, if you have a very big rat or very active rat, you can use the steel jacketing, which is much less flexible. And if you find the monocoil too inflexible or too heavy for mice, you can use a non-armored cable, which is very, very flexible and light. So you may have noticed this connector on the compact LED is different from the one on the tabletop LED. So this one is the LC connector. This one is the FC connector. This is not to be confused, again, with the FC ferrule and the LC ferrule. So for clarification, this patch cable has an LC connector with an FC ferrule. And this one has the FC connector with an LC ferrule. And you can get any combination of the two. We do offer compact LEDs with the FC connector. If you're using a patch cable from a different company, this connector is likely going to be compatible, or if you just want that screw connection. But what if your experiment you can't use or don't want to use a patch cable? So this is when you can try the head-mounted LEDs. This is 1.5 gram LED, which will connect directly to the fiber stub implant. And this one I'm showing has an FC ferrule. This is not a completely wireless system. So there is a magnetic wire that you stick directly to the top of the LED and then plug into the commutator for power. And if you're using this head-mounted option, I do recommend a torque arm. So this is going to stick right onto the bottom of your commutator. And then you can shorten your wire and clip it to the torque arm to make it the correct length. Additionally, the torque arm reduces the force needed to spin the commutator. And then again, you can turn on your radiant pattern stimulation. what if none of these more traditional wired systems work for you? Well, in that case, you can try the completely wireless HELIOS LED. So this is 2.5 grams, and this particular one has an LC ferrule. And it will communicate with your, excuse me, 4-channel driver through infrared signaling. Now, the weight of this LED is counterbalanced by battery life. And so the HELIOS LED is only recommended for experiments that last less than 3 hours. However, the exact battery life will depend on your stimulation pattern, and this is something you're going to want to calculate prior to deciding to use a HELIOS LED. So once you have chosen your hardware setup, the next thing to do is integrate it with your existing behavioral setup. So in this example, I have an operant chamber and a behavioral camera, which is part of the Stimulation system, which is Plexon's dedicated behavioral tracking system. And so what you'll want to do is send digital outputs from the Plexbright. Typically, these are called TTL pulses. You'll send these as timestamps to your behavioral system to mark light delivery. Many of you actually indicated you wanted to do the reciprocal and actually send triggers to the Plexbright system to trigger light delivery when a particular behavior occurs. So good news, this actually can be done in 3 simple steps. The first is to connect the hardware, because it is the hardware that will generate the TTL pulse. Then you need to tell Plexbright how and when to send these digital outputs. And then you need to tell your receiving behavioral setup, or Cineplex, to expect these TTL pulses and to record them. So I'm going to talk mostly about the hardware setup, and then Damon will talk a little bit more about setting this up in the software specifically. So on the back of the 4-channel controller, there are digital input and digital output connectors. Oh, wrong way. One of the connectors you can get from Plexon ends in bare wires. And these bare wires will connect directly to a Sennheiser trigger box. So in Sennheiser version 5, the trigger box acts as the relay for all the digital inputs and outputs. So the 4-channel controller can output 4 different digital signals. These are running, non-zero, zero, and not running. And these are all referenced to the current or voltage output from the 4-channel controller. Now, each of these 4 digital outputs for each channel is mapped to a single pin. And by pin, I mean the physical metal connection in the controller connector. So selecting which type of digital output you want or which channel is a matter of simply finding the correct pin and then finding the correct corresponding wire to plug into your Sennheiser system or other behavioral system. The pin maps can be found in the Plexbright user guide, and then the pin to wire maps are sent with the connectors themselves. The final step is then to tell Sennheiser or your behavioral program to expect these digital inputs and then to record them. Now going the opposite direction, from the Sennheiser behavioral system, sending a digital output to the 4-channel controller to control optogenetics is almost exactly the same, except now you're sending behavioral events as digital outputs through the trigger box, through that same bare wire cable that's now connected to your digital inputs. Like the digital outputs, the digital inputs to the 4-channel controller, the TTL pulse will do something different depending on which pin is receiving it. However, different from digital outputs, the exact function of the digital input can be modified and refined in the Radiant software. So in addition to connecting your Plexbright Optogenetics to your behavioral setups, many of you also indicated an interest in integrating optogenetics with a neuronal recording. So I'm going to discuss integrating optogenetics with the optical recording technique vibrophotometry, and Damon will go into integration with electrophysiology. There are vibrophotometry systems that have integrated optogenetics and vibrophotometry recording that can be done through the same fiber. However, if you don't have one of these systems, you can still use these techniques in tandem. And so the hardware setup is going to be almost exactly the same, connecting the 4-channel controller through digital inputs and outputs to your vibrophotometry system. And Plexon's vibrophotometry system also has a trigger box. Now, if you want to do single region dual optogenetics and vibrophotometry with 2 tandem systems, you'll need to put at least one fiber at an angle, most likely. And for this, I recommend looking into tapered fibers, which are a type of fiber that Plexon offers, because these emit light along an entire active length. One setup that might actually benefit from doing tandem systems is if you're looking at circuit dynamics across multiple regions. So you can do optogenetic stimulation in one region and vibrophotometry recording in another region. Now, no matter if you're doing vibrophotometry and optogenetics with tandem systems or with a combined system, there are three main considerations that you should think about when doing these techniques together. And the first is the excitation and emission spectrum. So here I'm just showing generalized excitation and emission spectrums for a green fluorescent indicator like GCamp, and then a red fluorescent indicator like a red-shifted dopamine indicator like Neurolight. So if you're doing optogenetics, you need to make sure that your opsins don't overlap, the excitation of your opsins don't overlap with either the excitation or emission spectrum of your indicator molecules, because this will then produce artifacts in your vibrophotometry recording. So the spectra is something you need to consider very carefully when doing these dual optic techniques. And the next consideration is power level, because vibrophotometry uses microwatts of power, whereas optogenetics aims for milliwatts of power. And part of the reason you need the different power levels is because of the excitation protocol that you use for the techniques. So in vibrophotometry, you need a constant excitation of the region of interest to be able to capture when the indicator molecule, like calcium, is actually present. Whereas optogenetics, you do short, very high amplitude bursts of excitation to maximally activate all the opsins in the region. So before we move on to Damon's presentation, are there any questions? Nope. Okay. Looks like we're turning it over to Damon.
Alrighty, thanks, Kristen. All right, guys, so now that we have a solid understanding of the various options and components that make up Plexon's system, the opto stimulation system, I'm going to touch on how some of these components can work together and actually integrate with some other systems. So specifically, many of you reported that there was interest in combining opto stimulation with electrophysiology recording, and further information about interacting with systems via digital inputs and outputs. And as Kristen showed, this can include behavioral control systems like Med-Associates, Lafayette Instruments, Colburn, et cetera, as well as some video tracking systems that Plexon offers as well. So I'm going to give an overview of some of these. And as you'll see, as we work through this, there's seemingly innumerable possibilities for these different types of interactions. So I hope here to sort of plant a seed with a few examples in hopes of engendering further discussion offline for those who are interested, to kind of get into the nitty-gritty of the lab's exact details and requirements. So we're going to start here with the system component overview, and we're going to come back to this a few times here, but initially you'll see the commutator here in the middle, and rather than the opto only commutator that Kristen showed in the behavioral examples earlier, this version offers a means of connecting our digitizing head stages for ePhys recording to our Omniplex ePhys recording system, as well as the 4-channel controller that controls the compact LEDs. So we have several models of commutators available, including both motorized or non-motorized, depending on animal model, and you can support anywhere from 1 to 4 recording head stages in addition to the 2 compact LEDs. And just since we're talking about head stages at this point, the commutators can the head stages can support anywhere from 8 channels individually all the way up to 128 channels. So there's quite a bit of flexibility here. As far as the connectivity goes, you'll see here in the red circle the male Harwin connectors that are used to connect our digital head stages, as well as the 2 magnets and power for the compact LEDs. So looking back at our component overview, just as Kristen said, you'll see the 4-channel controller connected to the commutator here. And she also mentioned that the 4-channel controller box is configured and controlled with a software program called Radiant. So Radiant can provide both current or voltage, depending on your light source. But as Nafi said, because we mostly specialize in current-driven LED modules, I'm going to start here with the output device as LED. This is an actual drop down in the software. So if you wanted to use our software and hardware interface with a different light source, that can be done as well. Directly underneath the output device, you'll see a drop-down menu of various wavelengths, and conveniently, the maximum recommended current is listed as well. So we'll see in a moment an example of how the software responds when we exceed the recommended current value. So with my output device and wavelength selected, I'm going to leave it as is in this manual mode. And just as you would expect, this is going to provide a simple GUI controlled constant on at the current output selected. So now for the next section, we're going to want a bit more flexibility in controlling our stimulation pattern. And for this, we're going to go in the drop-down menu to select pattern generator rather than the previous manual mode. All right, so here in the middle of the GUI is the pattern generator, and this is going to provide the user with a lot of flexibility in designing the stimulation pattern. This can be simple square pulses and ramps to quite complicated arbitrary waveforms. But in this example, I've defined a simple ramp pattern for my 2 LED modules on my commutator. And so first, I'm going to stop the ongoing manual mode stimulation that we were just doing and switch over to pattern 1 that we defined, that we just discussed on the other one. So here, sorry, wrong computer. Here we go. So we have 2 LEDs, we've selected pattern 1 for each of them. And the pattern that I've defined is an initial ramp from 0 to 300 milliamps over the duration of 1,000 milliseconds. And then the second, I have a falling ramp, just doing the opposite. So going from 300 milliamps to 0 over the same time period. So as I mentioned on the previous slide, when we exceed the recommended current, Radiant actually has built-in protection to let you know that because our orange LED cannot handle the same 300 milliamps that the green LED can, it's going to automatically decimate the current provided to provide protection. All right, so here is just a quick example of the two ramps playing on a rotating green and orange LED. All right, so back to our system component overview one last time. So now that we've seen how the Ephys signals are routed through the system and the commutator, and how the opto controller and Radiant work together again with the commutator, what's the next step that we can take for further integration? So what we're going to be able to utilize our video tracking system along with the trigger box that Kristen mentioned to send TTL events, digital inputs to trigger the onset of stimulation, the onset of that pattern generator that we've already defined, as well as sending TTL events to our Omniplex digital input board to annotate. This will allow us to annotate our neural recording with the times of stim onset, for example. So in this example, this is a screenshot of one of our video systems. The video system is going to send out an event each time the animal enters this circular zone in the middle. The pulse is going to go to trigger the predefined stimulation pattern with the digital input, just as Kristen explained, as well as go to our Ephys Omniplex digital input board. So as you're recording your neural data and using your spike sorting of the Omniplex system, you're going to see these various tick marks. This represent the events that are coming into our digital input board from the video system and the trigger box. So using this either online or offline, one of the things that we see often done are things such as peri-event histograms, in which spiking activity can be viewed pre and post the onset of stimulation. So finally, Plexon now offers the Neurolight optoelectrodes, which integrate 32 Ephys recording channels with 12 channels of micro LED stimulation within this single 4-shank electrode array. So when using this Plexon Neurolight stimulator and associated software, you can control the 12 micro LEDs in place of the previously discussed 4-channel controller and, for example, the compact LED module. So these integrated micro electrodes and the Neurolight stimulator will take place of those. And as you see, we have one of our dedicated types of commutators to support the Neurolight stimulator and the dedicated stimulating head stage that controls these micro LEDs. So rather than going into a lot of the detail here, we have a multi-part webinar series available on our website that we did a little while back. So if additional details about the use of this Neurolight technology is of interest, I would encourage you guys to look that up. And of course, reach out to us with any questions as well. So any questions about the integration, the Ephys recording, digital video tracking, etc.? Alrighty, well, thank you very much.
All right, so if there's any just general questions, not just for Damon, but for overall for the Plexbright system, if you guys have any of those, you can ask now. We'll wait a few minutes and see.
I have a general question. So definitely, like, I think, sorry, I don't recall who was Nafi maybe for the first presentation, was talking about using LEDs certainly for like a 470 nanometer with halo-rhodopsin, but traditionally in the literature and sort of word of mouth is that you need a laser for the strength to activate something like RK-rhodopsin or halo-rhodopsin. So I guess I'd just love to hear from you guys, you know, in the technological advances in terms of like customer satisfaction and anybody else here that's actively using LEDs just to use to work with inhibitory strains. Is that just like common practice now?
And this is directing this towards the audience. So,
I mean, I guess the Plexon team, but if anybody else.
yeah. So no, we do have some people using LEDs with RK-rhodopsin. I know actually too that the response curve is only kind of more. It's actually, of course, it keeps getting elucidated, and they're getting people keep kind of getting more accurate results. It's only really recently been really accurately mapped out. So beforehand, it looks like people were basically kind of had a wrong idea of where the peak waveform was, and so since they weren't stimulating, since they thought that the peak was at the wrong one, when they would try to use a lower light source, they weren't getting robust behavioral responses, and so they just assumed you need a lot more power. Much more recently, it's kind of gotten mapped out better, and so people have been able to successfully get good robust responses using LEDs. There's actually a good resource I have on my computer here. Do any of you guys use it's the Adgene, the plasmid repository? They kind of they have a nice table on their website that kind of shows where the most the preferable wavelengths are for all the proteins that people are commonly using, and they are continuously updating as new publications come out.
I'll put the link to that page that he's talking about in the chat if anybody's interested.
Thanks, Kristen.
Great, thank you so much.